Next, I want to talk about the fluid pressure. Um, Generally, there are different type of fluid that we can deal with. For example, we can deal with the water as a fluid, or air as a fluid, or oil as a fluid, and different type of fluid. Here, specifically, we talk about the water. Is a easier fluid to work with, and one of the reasons that it's not compressible, so its density doesn't change when the pressure changes. Whenever we talk about the fluid pressure, basically the fluid pressure can be calculated. The P is equal rho g z, and when we are dealing with that, the P is the pressure and always is at Newton per square meter if you are dealing in the metric, or if you are dealing in US customary is going to be pound per square feet, so or either it's going to be pound per square feet, so it's going to be either this one or that one. Rho is the density uh, that we are working with that, and then we have the Z is going to be G is the gravitational acceleration, and Z is the distance from the water surface. Distance from water uh, surface. So for water, when we are dealing for the water, the density, the rho, is 1000 kilogram per square per meter cube, or it's gonna be that 62.4 pound per cube, and the G is 9.81 meter by square second, or 32.2. So that's values that we are using in that equation P. So rho g. Remember, sometimes the rho g would be showed by gamma. So if you see the gamma, it's just the rho g, and it's called the it's the specific weight. So sometimes they just show it with that. One point about the pressure is that this is a very important point, is that remember the pressure is always is normal to the surface. So anytime that we have anything is under the water, pressure is always normal to that surface. So assume, let me draw here the water surface. I assume this is a water surface. I remember it's very common to show the water surface with that upside down triangle, and then we have a body sitting down there inside the water, somewhere in that water. So the pressure on that body is going to be always normal to the surface. So any surface we have, the pressure is going to be normal to that surface anywhere. So any point of that we choose is going to be normal to that surface. It's always be like that. So remember that anytime that we have an object under the pressure is always normal to the surface, regardless of what direction it has. Another thing is that how we define that z value, the z value we have, and says that if again I go ahead and draw the water surface here, and if I consider any point under the water, then the z value is the distance from the water surface to that point. It's going to be the z distance. But sometimes it might get confusing. Here in this case, we're clear that there's a water on top of that, but it doesn't matter if there's a water on top of that or not, as long as it's under the water. So let me draw a container here. For example, if I have a container like that, and I fill it with the water, and that's the water surface. I fill it with the water, so that's the water surface. It's completely filled with the water. And then I have I want to calculate the pressure for these points sitting here. You see that's the very small amount of water on top of that, but it doesn't matter. We always calculate the distance to the water surface. It's not important that there is a water on top of that or not, as long as it is under the water. The z is calculated from the water surface. The same here if I go ahead and draw another shape here, for example another container, and it goes like that, and then it goes up there, goes back like that. And if it's filled with the water again up to this point, and then I want to find the pressure applied at that point, again it doesn't matter there's a water beneath that, next to that, or there's a little bit water on top of that. All we need to know is that we always calculate the z from the water surface. So it's always the z would be from that distance to that distance, from the water surface to the location of that point. So no matter there's a water on top of that or there's not a water on top of that, as long as it is submerged, it's under the water, the z always calculated from the surface of the water. Now let's look at how we can calculate the water pressure on the flat plate. If we have a plate sitting under the water, assume that's a plate sitting under the water, and we have the water surface here and the xy axis. So there's a water surface on top here, and that plate sitting down there. We want to see how it's going to be pressure apply on that. If we assume that plate is sitting in a way that the pressure on the width is not changing, only on the length of that is going to changing. So we'll go ahead and calculate pressure. So pressure at this point is that if we go ahead and assume this uh, height is z1, this is the z1, then the pressure on top of the plate here, p1, is going to be rho g z1. The same for this part here. If I go ahead and say, assuming the water, the distance to water surface from here to the bottom of the plate is z2, then the pressure here is rho g z2. So we have the pressure on the top, and we have the pressure on top. So look at here, if we assume on the pressure changing on the length of that plate and it's not changing on the width of that plate, we can go ahead and convert it to 2D. So we have the 3D, and then we can convert the 3D to 2D load. So if to show how we can do that, I just draw this edge because assume the pressure only changes on this edge. So I will draw that edge here. If I draw that edge, and with the, we know that the length of the L and the width of the B, and then if I put the pressure on that, I want to make it 2D. So, and remember, the pressure is always normal to the surface. So if I have this, and it's all because the pressure is related to the z, so it's always going to be smaller on the top, it's going to be larger on the bottom, and have something like that. So this is the pressure. At this point, you remember when it says in the distributed load, when we want to convert a 3D to 2D, if there is no changes on the width, you just times the load by the width. So it's going to be this one, the W1 is going to be P1 times the B. So it's going to be rho G Z1 B. So that's the load there. And it's going to be in Newton per meter. So remember, the pressure here is in Newton per square meter. Same here is in Newton per square meter. But here it's become Newton per meter. The same here, the W to here is going to be W2 is going to be P2 times B, and then so it's going to be equal to rho G Z2 B, and whatever the magnitude is going to be, again, is Newton per meter. And then when we have it in 2D, we can go ahead and says, okay, there would be a resultant force applying on that. So that resultant force would be act somewhere here, and we can find it. So when we are dealing with the gate, the flat gate under the water is always you have the trapezoid like that, and the pressure is going to be on like trapezoid, unless the top part is at the water surface, which then this value becomes 0 and it convert from the trapezoid to just rectangle, because this part is going to be 0. So I'm going to just draw a very simple shape to show that how we can calculate this. Remember that we have a distributed load here. Well, we can either work it as a trapezoid, or we can always separate it in two distributed load, because the 2D distributed in a rectangle and triangle, and then do that. Now let me explain. If we have simple, I would draw that, and we can use it for any other cases as well. So assume we have a single vertical gate with a draw it this way. So assume I have vertical gate. And this distance is h, and then there is a pressure applying on that, or the force applying on that, and the value here is a, the value here is b, and if we want to do it in the trapezoid way, so we know that it's going to be the resultant force going to be somewhere here, it's going to be the Fr, and then the distance it has it, assume I would show it with the c, so this distance here, assume this distance is also c. So the Fr, the magnitude of that resultant force, is just the area of that trapezoid, so it's going to be a plus b divided by 2 and times h. So that's basically the area, and that c, where it's going to be located, where it's going to be active, that force is going to be 1/3 of, is going to be 2a plus b divided by a plus b times h. So that's where the location of that resultant force, and then you can do the calculation, or you can just apply it in any other angle. That's how we find the water pressure on the flat plane. Now let's look at how the water pressure is going to be on the curved plate. So um, if we have a water surface here and then we have a curved plate sitting underneath of that. Um, we know that the water pressure is going to be always normal to the surface, and so for example here it's going to be that much, and then by increasing the depth it's going to increase, its magnitude is going to increase, so it's going to be normal to the surface and it's going to keep increasing as we go down to the depths, and in every section is going to be normal to that surface, so eventually we have something like that. So this is the pressure we will have. Here we will have, I only draw the front faces, so it has, this plate has a width of, for example, like um, uh, B, so it has a width of B on that, also normal to the screen. So we know that the top surface, if I want to calculate in the 2D format, and not in the 3D, so we can do it into 2D. So you know that the magnitude of here, the magnitude we have here is W1 is the pressure at that point times the width of the plate, and so it's going to be rho g z1 times the width of the plate, and the z1 is the depth to that point, so it's going to be, that one is going to be z1, so the depth from water surface to that point. The same here for the second one. If we have the z from here to here, so it's going to be z2. Then the magnitude of here is the pressure at point. So the magnitude of load here is the pressure at point 2 times the width of the plate, and the pressure is rho g z2 and times it. And remember, we times it by b, so we can, instead of consider it as a 3D condition, we just consider it as a 2D condition. So we bring all the pressure in 2D in the front surface of that. Now, if we have that, it would be like that we might have the resultant force applying somewhere there. And one way of doing the calculation is that we have to go ahead and look at this distributed load. So we have the distributed load. The magnitude of that resultant force is the area of that distributed load. And the location that is going to be act on that is the centroid of that distributed load. So we have a distributed load like before, is a 2D distributed load. And the area underneath is the magnitude of that resultant force, and the centroid of that is the location that is going to apply. But there's another way, that's most likely is easier way of doing that, and we will use that for our calculation. Is that, again, I'm going to draw this same plate here. So assume we have it sitting under the water like that. All this. So we want to look at it how it's going to work. In this way, before we are doing that, one thing we will do is that we draw a vertical and horizontal line. So we start to draw a vertical and horizontal line here, and then the vertical line here. And then we'll go ahead and put the pressure on those lines. So whatever pressure applies on these horizontals, let me name them so it's going to be easier. So if I assume I name them, it's going to be A, it's going to be point B, and assume this point is going to be D. So the pressure applied on the BD is the weight of the water above the BD. So the pressure on the BD comes from the whatever we have above that. So it's going to be constant pressure, something like that. And the magnitude of that again is going to be W1 is going to be pressure at point 1 times the width of the plate. And it's going to be constant because the Z. And this load, it comes from the pressure in this column of water. The column of water is about the dB. Also, we have the horizontal pressure applying here. And that horizontal pressure is going to be like that. And started from here and linearly increase to here. So we'll have something like that as well. And this one again here on the top is going to be W1. So it's going to be the same because they are at the same height. So this one and this one is going to be the same because both are the same one. And this one is going to be W2, which is going to be P2B, and you can calculate it like the way we have it here. And this is the horizontal force that applied by the water. And then we have the water, the weight of the water is between A, B, D. So whatever water is there, also its weight is going to be applied on that gate as well. So when we have something like that, we can go ahead and replace the forces. So I will go ahead and say I can replace these vertical forces with the F vertical. So it's the vertical force is a resultant of this distributed load. Then I have the horizontal forces here. The horizontal forces here is as a resultant this trapezoid force applying on that. And then I have the weight of this body, so which is going to be applied on its centroid, and it's going to be the weight of um, ABD. And we know that the weight of the ABD, so the weight of the ABD is the area of the water we have times the width, which gives us the volume of the water, times the rho g, which gives us the weight. So it's going to be the area of the ABD, which gives us the front face area, times B, which this is going to be the volume, times rho, which is going to be the mass of the mass is in that area, the mass of the water, times G, which gives us the weight of the water is there. And then we have these three forces, and we just apply these three forces to get the resultant forces that we want. And then again, if the resultant force is going to be applied somewhere there, so it's going to be resultant forces, and we know that the magnitude of the resultant force is going to be a square root of that, the horizontal force squared plus the vertical force, which is going to be Fv plus the weight of the water in ABD squared. Then we take the square root of that. And the angle is going to have, the angle that force has, if this is going to be theta, then the theta would be tangent inverse of the vertical values, so divided by horizontal component. And if you want to find the location of that, the way we will do that is that, well, we will do it in two stations, so in two steps. So in one step, we calculate uh, the moment created by FH plus the moment created by FV plus the moment created by weight of the water above the gate. In step 2, we calculate the moment created by Fr, um, and we will call this one M1, and then we call these two M2. The M1 and M2 should be circled, so to find um, location of Fr, we will use the M1 should be equal to M2. So because whatever moment the M1, whatever moment the FV, FH, and the weight created, the resultant force should create the same moment. So for example, if I go ahead and calculate the moment of these FH, FV, and W about point A, and then I calculate the FR moment about point A, both they should be the same. So that's how we do that. We calculate the moment of these three forces first, then about 1 point, and then we calculate the moment of the FR about the same point, and then we just equalize them, and then we can, by doing that, we can find the location that the FR is gonna apply on that location. In general, there are two types of problem that when we are dealing with the curve gate we will deal with, and I will show you them. So the first one is that if we have, assume we have a wall, and then, so assume we have the vertical wall here, and then we have a gate, or the curve plate, and then we have the rest of the wall down here. So basically in that case we have the water right on top of the gate. So there's the water on top of the gate, like what we have. So let's see what happened here. The same as before, again we go ahead and we draw the horizontal and vertical line, and then we put the pressure on those ones. So we have the horizontal pressure here, and then we have the vertical we have the vertical pressure here, then we have the horizontal pressure here, and then we have the weights, and we can go ahead and we replace them with the this is going to be our vertical force, this is going to be the horizontal force, and then we have the weight as well. So it's going to be weight. We have these three forces applying on that gate, so we can use those three forces to find the resultant force. Similar to that, let's see what it can be a very similar case, but in this case we have the gate sitting at the water surface, and then we have the wall down here. So in that case we have the water surface, so the gate is at the water surface. The difference with the previous one is that, again, we go ahead and we draw the horizontal line, draw the vertical line, and then we start to put the pressure. The thing is that here we don't, because it's sitting at the surface, the z is going to be 0, and therefore the pressure is going to be 0. So there's not going to be any forces applying on that vertical line here. There's nothing there. And also on the horizontal forces, it starts from the 0, because at the water surface, the pressure at the water surface is always 0, and it keep increasing. So we will have a triangle like that, and we don't have anything up there. So if I go and put the forces there, so it's going to be we have the FH, and the FH is this times triangle, it's not the trapezoid, and the FV is going to be 0, and then we have the weight of the water in that area, uh, above that gate, exactly in that area that's surrounded by a dashed line and the gate. So these are the cases that we have the water right above the gate. So if there's a water right on top of the gate, how we will deal with that. The second type of the problem we will see, and said, so this is the first type. So there's another type of the problem for the curve plates. So let's again assume we have the wall again here. And this time we have the gate to be on the other side of the wall. So it's going to be the gate sitting like that, and then we have the wall. And there's the water on top of that. So this time the water is beneath the gate, not on top of. There is nothing on top of the gate. The water is actually beneath the gate. So the same as before, again we will go ahead and we draw our horizontal and vertical lines. So again we draw that lines, and then we go and put the pressure on them. So the pressure here start from here and linearly increase like that. The difference between this one and the other one is that we have the pressure here, and this time the pressure is equal to the one here. So it's going to be larger, and also it's going to be look upward, rather than the previous cases that we have that the pressure was downward. This time it's going to be look upward. So it's the magnitude is the magnitude here. This one and this one is the same because they're at the same depths, and it's going to look upward. So if I put the forces, so then it's going to be at the FH, and this time the FV is going to be vertically upward, and then we have the W, the weight of the water in this area. So this is going to be upward. Now the other format is that if we bring this all the way up and put it on the surface, so see what happens if I have the gate sitting right on the surface, and then we have the wall beneath that. So again, this time the water is underneath of the plate, is not, and there is nothing above the plate, unlike the previous one. So the same as before, we go ahead and we draw the vertical and horizontal line, and then we will put the pressure on them. Again, this time the pressure on, because here is at the water surface, it start from the 0 and it increase linearly until you get to this point. So we have a triangle instead of having a trapezoid. And then we will have this one also. It's gonna be upward, the same as before. The magnitude of here and here are the same. And then if I go and put the forces on them, so it's gonna be the FH, and then it's gonna be the FV, and then here we have, or over here we have the weight of the water applying there. So the only difference here is you have this as a triangle, and here we have it as a let me bring it up here. So we have it as a so yeah. So here we have a trapezoid, here we have a triangle, and then in this case that there is no water above the gate, the pressure is applying, actually the vertical pressure is applying upward rather than downward. Okay, let's look at an example to see how we can calculate the water pressure on a plate. So here assume we have a gate that is sitting under the water in this position, and we want to find the resultant hydrostatic forces that apply on that gate. So the very first thing we can do is that I will redraw the gate here again, and then we'll put the pressure on that. And remember, this gate that we are working with, that it has I did not draw that, but it's normal to the surface. It has a width of 3 meters. So it's what we see here and in 2D, and it's going to be in third dimension 3 meter toward the screen. So here we draw that the AB, and I'm going to put the pressure first. I'll calculate the pressure on that and put the pressure on that. So we know that the pressure is going to be always normal to the surface. So we know the pressure here is going to be something like that. So pressure on this top word is, if I assume, if I say the pressure at point A is going to be rho G and Z at point A, which is going to be for the density of the water. If you consider density of water 1000, then times 9.81 for the gravity, and the Z here is just 2 meter from the water surface. And if we do calculate that magnitude, it's going to come out as 19,620 Newton per square meter. And the same here, if I go ahead and calculate the pressure at point B, it's going to be rho G and Z at point B, which is going to be 1000 for density, and then 9.81 for the G, and the ZB is the distance from water surface, 4 meter, and the result is going to come out at 240 Newton per square meter. Now that we have this as a pressure, and remember it's 2D, so it's a pressure, and this pressure also extends in the third dimension along the width of the gate. So we have to convert it from the 2D to from the 3D to 2D. So if we go ahead and convert the distribution from the 3D to 2D load, remember that basically what we had done is that we times everything by the width. So that's what I'm going to do. So I'll draw the gate again here, and then this time I would draw the distributed load, but we converted from the pressure to from the 3D pressure to 2D linear load. So the magnitude here, the W at A, is going to be the pressure at A times the width. Remember, every time we want to convert the 3D to 2D, we just times everything by the width, because we assume there's nothing changing the width. So whatever pressure we have here on top of the gate, that's the same pressure we have it throughout the width of the gate. The same at the bottom of the gate, that's the pressure we have all the way throughout the width of the gate. So the magnitude of that, so it's going to be 1960/20, so it's the pressure at B and times the width of the gate, which is going to be the 3 meter, and it will comes out at, if we do the calculation, it comes out at 558,860, and this time it is going to be Newton per meter, because we make it from the 3D to 2D, so it's convert from the Newton per square meter to Newton per meter. And here the same, the W at point B is going to be pressure at point B times the width of the gate, which is going to be that magnitude. The pressure is going to be 39240 times 3 the width of the gate, which eventually comes out as 7720 and Newton per meter. So from Newton per square meter to Newton per meter, so from 3D load we go to the 2D load. Now that we have everything is sitting at as a 2D load is here, it's much easier to work with that. So we know that the FR is going to be something like that. So just a quick reminder is that if we have a gate, or if we have a distributed load like the trapezoid load, and it's going to be A, and then it increases to B, and then we have the FR, and if we have this length is going to be H, and this distance here is going to be, this distance here is going to be, let's put it there, this distance here is going to be C, this distance. So we'll know that the magnitude of the FR, the magnitude of the FR is going to be area of the trapezoid. This is going to be this, and the location of the FR is going to be 1/3 of 2A plus B divided by A plus B times H. So we use this equation for here to find the magnitude of the FR, and it's if we need the location, find exactly where is the location. So if you're in this case, if I go ahead and says, okay, this is the also this distance, if I consider this distance as a C. So let me draw a line here. So therefore the FR, the magnitude of the FR is going to be equal to the area of the trapezoid. It's going to be WA plus WB divided by 2 times the length of that plate. So we need to find the length of that plate. And if you look at here the length of that plate, I can go ahead and say this is 60 degrees and this is 2. Therefore, these lengths, the length of the gate, I can go ahead and say that. Let me draw that again. So if I come here and say this is the length of the gate here, show it here. Or let me draw that gate again down here. So this is the gate. Let me draw it down here. So if this is a gate, so we know that this distance is 2, we know that this height is 2, and we know that this is 60 degrees, and we want to find this length. And so this is the length we will look for that. So the length of, I would call it the AB. So here the AB, if I want to find the AB, AB is just simply or I can write it easier. So I would say is that AB, that magnitude, sine 60 is equal to 2. So AB sine 60 is 2. So I can say the AB is equal to 2 divided by sine 60, which is gonna gives us the length of the AB would be 2.3094 meter. So I can come here and then times it by the length of the AB. So the FR value is gonna be the WA, which is gonna be this magnitude, 58,860 plus 117720 divided by 2 and times the 2.3.94, and eventually this would comes out the FR would be the magnitude of FR would be 2,896 Newton, and the location of that C value here, the C is also is gonna be 1/3 of 2WA plus WB divided by WA plus WB and times the AB. So therefore the C would be 1/3 of 2 times 58,860 plus 117720 divided by 58,860 plus 117720 and times 2.394, and it would comes out as 1.02 meter. So that's how you find the resultant force applying on the flat plate under the water. Now let's look at how we can find the resultant water forces applying on the curved gate. So it's very similar to the previous example, but this time instead of the flat gate we have the curved gate. Let's see how we can do that. So first I will draw the gate and I will put the pressure. I calculate the pressure for that gate. So if I go ahead and draw the gate here, and then put the pressure on that. So remember that again, we want to put the pressure, draw the horizontal line and vertical line, and then we put the pressure on that. So we have the pressure here, and then we have the pressure here. So on the top we know the pressure at the PA, so that's the pressure at point A. It's gonna be rho G ZA, which is gonna be 1000 times 9.81 times the Z for the point 8 is 2 meters, so the depth is 2 meters. So it would be the magnitude of that, it would be 19,620 Newton per square meter. So again, remember the width of the gate is 3 meters, so it has the 3 meter width normal to the screen. We always see the front face of that, but it has the third dimension. Here the pressure at this point is again exactly the PA, because they both has the same depth. So pressure here and here is the same because both are at the same depth. And here we have the pressure at point B, which is going to be rho GZ at B. It's going to be 1000, and then we have 9.81, and then we have the ZB, which is the depth here is going to be 4, and then the magnitude of that is going to comes out, the PB would be 39 to 40 Newton per square meter. And then we have to go ahead, and then here, as we said, I didn't draw the third dimension, but it's a 3D load, so it's the pressure on the surface of the gate throughout the width of that. But we want to convert this 3D load to 2D load, and to do that, as you remember, because we assumed the pressure is not changing toward the width, so whatever we have here is going to be constant at the width, so we just times all the pressure by the width. So I'm going to draw that gate again here. So this time yeah, we have the horizontal vertical line. So this time I'm gonna have the 2D load instead of the 3D pressure. So this load here, this magnitude of this load is gonna be WA, the load at point A, is the pressure at point A times the width, which is 19,620 times the width of, which is gonna be 3, and the result of that is 58860, and it's going to be Newton per meter, because we times by V is from the pressure, it comes to the linear load, so 2D load, so it's going to be from Newton per square meter to Newton per meter. The same here, so this magnitude here is the same as there because the pressure is the same, and then it increases here, and then down here we have the load at point B. It's going to be pressure at point B times the width, which is going to be, the pressure is 39 to 140, and times the width of the gate, which is 3. So eventually it would comes out as, if we do that, it would be 117 and 720 Newton per meter. Now we will put the forces. Now we'll go ahead and replace this with the force. So we know that here I would have the FH, and then here I would have the FV. It's gonna be FV, and then also I have the weight of the water in that area, in the ABD. If I call this A, B, and then D, so it's the weight of the ABD is also, so the weight of the ABD is also is there, so we want that weight as well. So these are the forces we will have. So for the F, for the vertical forces, so we have here the FV is just the area of this force, so the length of the BD times that the magnitude of the force. So we know that is the 2 meters 2 meter, so the magnitude is 58,860, and the length of the BD is just 2 meter. So if I do that magnitude, I will get 720, and this time it's gonna be in Newton. The FH is the area of this trapezoid here, so it's gonna be the 58,860 plus that 17720 divided by 2, and times this height here, which is going to be 2. So that magnitude of the FH would be comes out as 176,580 Newton. So the FV is the area of this rectangle load here. The FH is the area of this trapezoid load here. So this is just the area of the rectangle, area of the trapezoid, and then we want the area of that. We want the weight of that ABD. So we know that the for that the weight of the ABD is the area of the ABD times width times rho times g. So area times b gives us the volume, times the rho gives us the mass, and times the g, which gives us the weight. So the area of that, if we look at that area of the ABD, is the area of this square here minus the area of the a quarter of the circle. So we have, if you have the square minus quarter of the circle, the remaining is going to be the area of the ABD. So to do that, so it's going to be 2 by 2, so it's going to be area of the square minus the 1/4 of the, or quarter of the area of the circle, so it's going to be pi times 2 square. So that's the area of the ABD, and then times b, which is going to be 3, then times 1000, and then times 9.81, which the magnitude of that's gonna comes out as 25,263 Newton. So these are the forces that we have. So then we know that the resultant force is the square root of the FH squared plus FV plus WH A, B, D squared. So it's gonna be the FH squared. So the FH is gonna be 100, sorry, 176, 580 squared plus, then the FV is 117, 70, 20 plus 25 to 63, then a square. So it's going to be the horizontal one, and this is the all the vertical one together. So then the FR, the magnitude of the FR would be 227 to 10 Newton. And the angle it has, so we can go say the angle is tangent inverse of FV plus WABD divided by FH. So if you substitute the magnitude there, it's gonna comes out at 39 degrees. To find the location of that again, we can go ahead and just assume the forces that we have on that. So if I draw this here, so we know the forces and their location, so we know that there is a FV here, there is a FH here, there is a W here, WAB, D's here. So if I draw those lines, and I know that the FR is going to be somewhere there, so it's going to be the FR. So to find the location of FR, I can write the moment of FH, FV, and W about, for example, point A, and write the moment of FR about point A, and then whatever moment we get from, if I add all the moments from FV, FH, and W about point A, it should be equal the moment that FR created about point A. We can write the same equation of moment about point B. Whatever is the moment FR created about point B should be equal to the moment FV, FH, and W created about point B. So if you equalize those moments, it will give you the location of the FR if you need its location as well.